Thank you for the intro. So this is going to be a fairly technical talk about everything what we have done in the last 2 years. And I'm going to have a lot of links to external documentation or external videos. Don't try to mark those down, because at the end of the slides, they're going to be a bit.ly link to the slides themselves. So you can just download the slides. OK, we started out with this one idea. Let's create a language which is like JavaScript. I think that was a great idea, because in this new space where everything was brand new and nobody could understand anything really, at least one thing was familiar, the language. And as a result, it was really accessible to a lot of people, and we got the ecosystem really spinned up. So many people joined. And it's really hard to take track of what kind of libraries and what kind of frameworks and what kind of projects are out there at the moment. But probably it's time to improve that and change Solidity from not being like JavaScript, but something better. JavaScript has some of, as a result of having JavaScript as an influence, we had some of the limitations listed here. So for example, we have weird scoping rules. We were trying to guess a lot of intentions of the users. And the last part is probably the var. So I'm going to give you some examples here to show what I mean. So is that, does it work? Great. Is that valid Solidity code? Any guesses? It looks horrible. It actually isn't valid, but not for the reasons you would think. The reason it's invalid, because this I variable is redefined. So if we remove that, is this valid code? It's horrible, and unfortunately, it's valid. Any ideas what it does? It's really hard to decipher, but it returns 1. So that's one of the really bad examples. This other one is a textbook example of what could go wrong. What do you think? What is this for loop doing? Is this for loop finite, or is it infinite? The answer is it's infinite. And the reason for that is whenever we try to deduce the type of the variable I, we look at the shortest representation in where the 0 literal fits in. Because 0 fits in into 8 bits, the I is going to be a uint8. And since 256 is larger than 8 bits, this comparison will always be true. So this is an infinite loop. So these were like a couple of examples of why some of these legacy things we received from Solidity are a bad idea. And of course, we have worked in the last 2 years to get rid of most of these. You can try many of these new features by inserting the experimental pragma. And I would urge you to try it. Because if you make your code to work and compile with that pragma, then you're going to be set for the next major release, which is the 050 release, which is going to be a breaking one. You won't be able to do all this mess anymore. You have to write proper code. There will be a much longer explanation in the afternoon by Chris about all the features, step by step, what have been changing for 050. Is there anything else? Of course, there are a lot of other things. One really big topic, which unfortunately won't really make it into 050, is redefining inheritance rules. Inheritance in Solidity is really important, because we are composing contracts of multiple abstract contracts or interfaces. And a couple of questions we have there is, what about shadowing? What about when we redefine or override a function which is defined in the parent? How does that work? Are interfaces, interface contracts, which probably not many people have heard about, are those useful at all at the moment? Can we change visibility or mutability levels during inheritance? These are a couple of questions which have to be solved. And if you have a strong opinion or just would like to see the discussion, there's the link to check out. OK, what else did we do? So I'm going to list you probably 4 or 5 things here, which all have happened in the last 2 years, mostly last year. So the first one, the contract metadata. Has anyone heard about the metadata? Yeah, nobody has heard about it. That's really unfortunate. So the thing here is, for every single contract, we are generating this metadata, which is a JSON file. And that JSON file contains all the necessary information needed to recompile the very same contract and achieve the very same bytecode output. So, of course, this can be used to verify the contract. It can be used to verify that all the sources provided will result in the very same contract. So what are people doing right now instead of this? Usually they're using Etherscan and the verification tool on Etherscan. If the metadata would be adopted, you could have multiple implementations on Etherscan, other blockchain explorers, other tools to do the verification for you. The last important part there is we not only generate this JSON file, which explains all the details needed, but we also hash the JSON file and include the hash of that in the bytecode. That's the way you can verify that it actually corresponds to the right input. So if you want to get more into this, there's a link to the documentation. But I'm going to show you an example of what this JSON file looks like. So on the top, you obviously get the correct compiler version used to compile this. And these are all the settings which were used in the compilation. And these are all the sources which can be utilized. So notice there's a hash. In this case, we haven't included the actual source code used. We just include the hash. So it's up to the user to upload the sources to a relevant URL. This is possible because the BZZR, I'm not sure if you're familiar with that, but that's a URL to a swarm. So if you publish your sources on Swarm, and you publish this metadata on Swarm, then the system just going to work on its own. Okay, the next big thing, which is quite a big topic, is the SMT Checker framework we have. So it's a seamless way to verify safety properties. And by seamless, I mean that it's part of the compiler. It's not an external tool. You don't need anything else. You just need the compiler. And you can utilize all these verification steps. Some of the properties our SMT Checker framework can verify includes overflow, underflow, division by zero, and lastly, the most important one, it can check for user-specified assertions. I'm going to give you an example here. So this is a sample code, and we have enabled SMT Checker with this line. And it's going to give us a couple of warnings. What could go wrong in this piece of software? So first of all, it tells us that this is always true, and that means it's an infinite loop. And what is the reason it can think about that? Well, it's very simple. I is an unsigned int, and therefore it's always equal or bigger than 0. But a more interesting example is this one, which looks rather confusing. So let's decompose what the compiler means by this. So say it shows us that I, the decrementation of I, if we start off, so these numbers here are the state of the variables. And it tells us, is this the post state? No, that's the pre-state. So if we start with I, and we decrement it, we're going to end up with -1. But that means the end result also going to be 0, because it's an unsigned number. We cannot really go anywhere. So it would just tell you all these tiny details. Probably one last note on this one. Why is there a space and an equal? So that refers to the return variable. The return variable is unnamed. I guess this can be improved in the future, but you just have to understand what all those lines mean. Another example is the well-used safemath add operation. So let's see if our SMT checker can give us any indication that this safemath works or not. So it gives us an example case of input values where this statement is going to overflow. So it is telling us that if A is 1 and B is all bits set, then on an unlimited bit length, this is the value we're going to get. And if you count all the zeros, you're going to see that this is bigger than 256 bits. And the value we got here is 257 bits long, and the top bit is set. But since EVM only works in 256 bits, it's going to truncate all these values. So we're only going to have all these zeros, and as a result, C is going to be 0. However, the SMT checker is only a compile time feature. It won't include any kind of runtime check into the code. So you definitely still need to insert a assert statement, which will be part of the generated code. Okay, I'll give you another example. You can specify assumptions for the SMT checker. Probably everyone here has heard about the require and the assert statement in Solidity. The difference between, from a user standpoint, a require statement will do a revert, so it won't consume all the gas, while the assert will consume all the gas. But we can use these slight differences with static analyzers, verification tools, as well as the SMT checker feature we have. So here we verify, we set the assumption that A and B are going to be less than 256. And during runtime, we're going to revert if they exceed that. Since we have set these assumptions, the SMT checker can know that C can never go above 512. And therefore, it won't complain. OK, the SMT checker, unfortunately, as I mentioned, it's seamless. You don't need anything else. But unfortunately, it's not yet part of the JavaScript release of Solidity. So it cannot be used in Remix. You need to compile it yourself. And you need the Z3 or the CVC4 libraries first in order to compile it. But it should work seamlessly. The compilation should work seamlessly. And once you insert this experimental pragma to turn it on, it should just give you the proper warnings. There is a much better intro on this URL, which goes through step by step and explains all the reasons. One thing I wanted to mention here that unfortunately it's not widely used yet, but Augur has decided to use it. And they can actually they can compile the entire code base with SMT checker turned on without any warnings. OK, we did a couple of more things. So that's done with SMT checker here. So a quick intro into the ABI encoder. Probably everybody has heard about ABI here. But ABI actually means a contract ABI, which is a specification on how to encode data while communicating with a contract. And then as an example, for the ABI, we take this function, the balance function, which takes an input and returns an output. What happens during the compilation process is that we generate an ABI decoder code piece, which takes the call data and parses it and puts an address type variable onto the stack. Then it does whatever it wants to do and returns a number, which is the uint. So the other code piece we're generating here is an encoder of that stack variable into a return data. Currently, all of this is written, handwritten, with generating EVM bytecode in C++. As you can guess, that probably is quite a heavy process and requires a lot of effort to make it proper. And it's not the best way to do it. So we have decided to rewrite it. And there's this feature called ABI encoder v2. It's written in Youll, which I'm going to talk a bit about soon. It can, on top of what the current ABI encoder can do, it can ensure some safety properties. For example, it can detect if the input is too short and can reject the transaction. It can also validate more conditions regarding input values. So for example, it can validate if a Boolean only contains 0 or 1, would reject otherwise. But what's more important, I guess, to you guys, is it supports more complex data structures. For example, structs and multiple dimensional arrays. So the way to enable it is by this experimental pragma. However, it's not stable yet. So we wouldn't recommend using it in production. But we would definitely recommend in trying it in your test suite next to the current version and report any issues found. Because if nobody's going to test it, we're never going to be confident enough to release it. And we definitely want to release this feature into the main branch, because it's so much better. OK, and lastly, Youll is our new assembly language. Some of you may have heard about this when it was called Julia last year. But we have renamed it, and the current name is Youll. So it is an assembly language. And one of the main driving forces was that we want to have a process where we can audit the compiler code base with much better confidence and much faster. And with Youll, we can achieve that because I guess this was OK. So the way we can achieve that is we want to compile Solidity, your contract, into a representation in Youll, so compared to that, currently Solidity goes directly from Solidity source code to EVM. And that's like a really bad process. So we want to introduce this extra step in the middle. We compared Solidity to this Youll assembly, and then we compile it to EVM. But as an addition to that, if we have Youll in place, we can also compile Youll into other VMs. For example, we can compile it to WASM. So by doing this step, we're going to have support for the future. However, Youll was designed by the Solidity team. We don't really want to own it. We don't really want to limit it and restrict it to Solidity only. So we'd be really glad if other projects, other language teams would try to adopt it. So for example, if Viper would decide to compile to Youll instead of what they're doing currently, and currently they're compiling to LLL. So if they would compile to Youll, they would get EVM output, WebAssembly output, and they would get all the optimization features we have implemented in Youll. They don't have really any optimizations in LLL. So there's more documentation on the URL, and I would also invite you to watch the talk from DappCon, which confusingly is titled Julia, but talks about the same thing and explains all the features in Youll. OK, two more things we had in the last year. There was an audit end of last year, sponsored by Augur and done by CoinSpec. It has found 10 low-risk issues, 9 of which we have fixed a while back, probably in December. And there's one single low-risk issue outstanding, which is a proposal about the override keyword in inheritance. And that is, of course, part of the inheritance discussion, so it's not forgotten. There's a report there if you want to read it. But we have a second audit ongoing at the moment, which is done by the Zeppelin teams. And actually, we are working closely together with them. So whatever issues they identify, we can fix them up front. They haven't identified anything major, just low-risk things with tooling. So whatever changes we have done as a result of that improves the way people can get into contributing to Solidity. Because the way they wanted to understand it is how they can start work on Solidity and identify issues afterwards. OK, 2 more slides. The theme. So Solidity for a long while, for the 2 years, mostly have been only Chris and me, which worked out really well, but we were kind of slow in churning out new features. We did had a lot of external contributors, but they were coming and going. Some of them stayed longer than others. We were really lucky this year to grow the team. And we managed to grow the team into 7 people. The names are in order of joining. We had Eric, Daniel, Leo, Christian, and Chris. And now we have 3 Chris's, and we have no idea how to distinguish them. Some ideas, Chris 1, Chris 2, and Chris 3. But that's not the best one. We were lucky to grow the team, but that doesn't mean we don't want any more contributors. And contributing to Solidity doesn't mean that you have to write compiler code. We're happy to receive feature requests. We're more than happy to receive discussions on existing design issues and feature requests. But if you're not a coder, or if you don't want to get your hands dirty with language design, you can still improve the documentation, because the documentation can always be improved. But lastly, if you do want to get your hands dirty with compiler code, I would suggest to have a look at this tutorial, which has been made by one of our external contributors, Federico. And it gives you a step-by-step guide how you can get started with changing the compiler itself. It's 1 hour long, but I think it's worth watching. If you do consider to help out, I would suggest to look for issues labeled Help Wanted or Good First Issue. And you can also find a lot of them labeled bounty worthy, and they would have usually a Gitcoin bounty attached. It's really great that we have so many bounties by Gitcoin, because we actually had, I think at this point, close to 10 external contributors joining through the bounties, and some of them stayed. So that's the link I mentioned. Please download the talk there and click on all the links. Thank you.